Hey, welcome in everybody. Happy Friday. Today we're going to have a slightly longer warm-up since today is a day without notes. And then after today's warm-up questions, we'll outline exactly what is going to be on Tuesday's mid-chapter quiz. It's going to be pretty short and light just because I'm not trying to like tank anybody's grades right before the end of the quarter. I just want to make sure that everybody's been doing their best to keep up. So the quiz on Tuesday will be fairly short and fairly straightforward. Make sure to use your time over this last 3-day weekend of the school year. Use it wisely and get caught up on any late work that you may or may not be missing. I did my best today to get the gradebook updated with everything I have. So yeah, anyway, it says due now at the top, and it has today's date at the top, but I'm going to scoot it up so that we can see all parts of every problem. And I'm not quite done with item 2 yet because last hour I was a little late in ending. Said lots of goodbyes to the seniors in AP Physics because today was their last day of school. If you know any seniors, be sure to hit them up digitally with a congratulations and a goodbye because, you know, today's their last day of school. Anyway, item number 1. I have this weird, like, off-center Black Widow shape, this hourglass inscribed within a circle. And I think it's interesting that, and by the way, I'm sorry if it's a little unclear. I guess the A should go on the outside. These letters name the points. So I'm naming some points A, B, C, D, E. And here's what I'm telling you. The measurement of angle CAB, which is right here, is 29 degrees. And measurement of angle EBD, which is right here, that's 140 degrees. And there is actually enough information here to solve for every single angle, as well as every single arc measure. Do it any way you would like. There is a trick to this. There's one angle that might be hard to get, but to give you big hint, I will say this. That's all I'll say. That's the only hint I'll give. And then item number 2, I'm not quite done. Let me finish designing it real quick, and then I'll go through it. But I think there should be plenty here to chew on. At least copy the diagram down and get those numbers. How's it going out there?
Good. You?
I'm good. Yeah. I think today I'm going to take my bike to the bike shop and have them tune it up because the weather's getting, I mean, the weather's always nice in LA, sure, but with work ending and with the weather getting nice, I think I want to take the bike back out. So I think I'm going to take it in and get it like greased up and get the cords tightened for the season or whatever. So I don't know, I'm excited. Probably going to ride over to the bike shop with my bike with a skateboard in my backpack because I think the bike will take a couple days. So I'll leave it at the bike shop while they fix it, and then I'll ride my skateboard home. Also, the bike shop near my house has a restaurant, so I'm also picking up lunch. They make really good sandwiches. It's a really cool little business. Okay. For item number 2 here, measurement of angle NPL, which is this angle, is 87 degrees. LN is not a diameter. MN is equal to 4.6, so this length here, that's 4.6. LN, which is not a diameter, right? But LN, this length right here, is 7. And what I want to know is, what is LM? And with that question, it's easy once you know how to do it. However, the hard part is figuring out what methods I'm actually asking you to utilize and use. Use whatever information we have from yesterday to label as much information onto this diagram as you can. And then I think the correct solution technique kind of emerges, it kind of is natural once you label everything you have on there and think about the way that this chapter interacts with what we studied last chapter. What did we study last chapter?
Trigonometry.
Yeah, so this is actually a trigonometry question. Think about the techniques that we have, the methods that we would have to use in order to analyze this. I'm going to give you all 2 minutes. I'll be right back. I'm going to go get a cup of water because, like I said, I was a little late ending AP Physics, and then I went straight into writing this warm-up, so I didn't get that like 5 minutes in between. I'll be right back. Feel free, of course, to talk amongst yourselves if you guys are working on this problem and you want to ask each other questions.
Does anyone's screen have like?
Yes, it's
Yeah, I can't see the question.
Yeah, I can't see anything.
I blocked it.
What is that? I think it's headphones or something.
Oh yeah.
It might be a.
Hey, super sorry. I'm super dumb. I should have known that hanging my headphones on the lamp the way that I normally do blocks the questions. Heck. All right. Y'all ready for this?
Yeah.
Yeah.
Okay. So, like I said, item 1, based on those 2 angles and those 2 angles alone, along with the rest of our geometry, there's actually enough information to define all of the angular parameters of this orientation. And actually, it would also be enough information to figure out every length if you were given just one of them, because that's kind of what math lets you do. It lets you start with some minimum amount of information and use rules to extrapolate out to the maximum amount of information available to us. So this here is 29. And this here is 140 degrees. And let's begin. What are some other angles that we could figure out pretty quickly?
We can get DEG. You could say that's also 29.
And that is actually the key, and that is what's with the hint. This must be 29 degrees, and I bet right now, depending on like how much of the homework you've done, that may or may not be obvious, probably not obvious. Why? How come it has to be 29 degrees?
Because if you look at the arc that it's creating, it's the exact same as the arc that the CAD or CAB is creating.
So yesterday, that is perfectly correct. Yesterday, that thing that we learned is called the inscribed angle theorem. If this angle is 29 degrees, what's this arc measure?
58.
Yeah, about 58. Yeah. It has to be doubled.
It has to be doubled. So from 29 to 58. And if this is a 58-degree arc measure and this angle also inscribes it, then this has to be half of 58. So by the transitive property, any 2 inscribed angles which intercept the exact same arc, they themselves must be equal. So now that you have this, I think the rest is easy, because how do we do stuff in a triangle? What's this?
Third angle. You can just do third angle theorem for all of
Yeah.
them.
Yep, third angle theorem. So who's this? What angle measure?
That is
11.
yeah, 11.
And again, over here, we could use third angle theorem, or we could realize that this intercepts arc AE. This also intercepts arc AE. So this has to also be 11 degrees. And so what's this angle right here?
140.
140.
Okay. And if this is 140 and this is 140, that adds up to,
280.
280.
280.
and a full circle should have how many degrees in it?
360.
So it's 360 minus 280.
80.
Now cut that in half.
40.
So this is 40 and this is also 40. So that's all of the angles on the inside of the little hourglass that we made here. And now let's also figure out all of the arc measurements. So if this was 29, this goes out and is 58. And so if this is 11 and this goes out, this is,
22.
yeah, and you'll notice this isn't drawn to scale. I didn't measure this one with a protractor. I just made these numbers up. I actually think these two digits are flipped. If this is bugging you, if this is a bigger arc measure, it should be bigger than that. I think these two values got flip-flopped. Oh. Can we get those other two arc measures?
Yeah.
Aren't they like 140?
Yeah. Because it's like central. Because it's like the central angle, that means it's gonna be the exact same. It's not inscribed.
Wait, but is it the center? Is it the center point?
No, this is not the center point. I actually think it might not be
Oh.
possible to get what
Yeah.
CA and DE are independently. I think we can only know what their sum is.
Oh, I thought that was the center point because like the dot kind of made it look like the center point.
No, no, no. If it was the center point, then this would be even more boring because then it would be a diameter. Then it would mean that all these angles were 90.
Yeah.
Interesting. I don't think there is enough information here to get CA and DE. I think I would have had to have given you another degree of information. Huh. That's
So
weird. Yeah.
You can only find their sums.
Yeah, all that we know is that arc CA plus arc DE, what do they have to add up to?
280.
Yeah.
Yeah, they have to sum to 280 because this is incomplete. If anybody finds a way to actually get these individually, I'll give you extra credit if you figure it out and email it to me. I don't think it's possible, which is interesting. Is that okay for item 1?
Yeah.
I think that's all we can do. Huh. I'm disturbed. I thought this was...
So it's not an inscribed angle either?
This is an inscribed angle, 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 all this in the middle, not inscribed angles because these don't sit on the edge.
Yeah.
Yeah.
I'm gonna think real hard about this. Maybe it's one of those things where if we very cleverly add a radius, something happens. I will work on this and think about this more, but I believe this is as much information as can be squeezed out of it. Item number 2 here. I'm going to do the same thing just because I think labeling stuff directly onto a diagram helps a lot with thinking in the brain, just so that you know what you have and what you don't have. So NPL, this right here, is 87 degrees. LN is not a diameter, and I'm just saying that explicitly so that we don't make bad assumptions about what some of these angles may or may not be. The length MN here is 4.6. The length LN here, the big one that goes across the middle, that is 7. And what I want is I want LM. I want this length over here. So what did we learn yesterday? What does this let us do?
We can get the opposite angle, which has to be 93 because the opposite angles are supplementary.
So for a quadrilateral inscribed in here, we had a special case yesterday where we were able to prove that if you have a quadrilateral inscribed within a circle, opposite angles necessarily must be supplementary. They have to add up to 180. Because in total, this angle inscribes this arc, this angle inscribes this arc. And so if this angle is 87, what's this arc?
93. Oh, the arc is thing. I just did it. 174.
That arc on the opposite side has to be 174 because it's double. So that is to say 87 times 2 gives us 174. But what do all of the angles in a circle have to add up to?
360.
360.
So that means that the arc on the other side, right, if this guy right here from there to there is 174, then this guy right here from here to here has to be 186. And again, if I know that this angle goes out and inscribes this arc, that this measurement has to be half of that number. So I take that, divide it by 2, gives us that this is 93. Saying that opposite corners are supplementary is kind of just a shorthand to give us the correct answer. But I think the logic is very followable if you take it step by step.
How'd you get a 174, Mr. Robinson?
If this angle is 87 degrees, the inscribed angle theorem says that the arc that it inscribes is double that measurement. So
Oh,
if this is
yeah,
87, then this arc, LMN, has to be 174, which means that the arc NPL has to be 186, which is what gives us the 93.
yeah. Okay, I get it.
And so now, instead of looking at the whole problem, instead of looking at everything in total, let's just look at this triangle, because we have lots of training in triangles, right? I have a length of 7, a length of 4.6. I actually need this other length over here, and all I have is an angle. So let's go ahead and run through our trigonometry playbook. Is this a right triangle?
Nope.
No.
No, which instantly means there is no useful Pythagorean theorem, there is no SOHCAHTOA. Instead, we have two techniques. What are they?
Law of sines and law of cosines. But we can do law of sines because we have an opposite angle pair.
Correct. It's either the law of sines or it's the law of cosines. And to differentiate the two, we check whether or not we have a pair. We do have a pair. The 93 goes with the 7 because they're on opposite sides of this triangle. And what is that going to let us solve for?
Angle L.
That will let us then solve for angle L because it is opposite of the 4.6 side length. So we're going to solve for angle L, and then we'll go from there. And as long as we keep working the problem and keep going and going and going, we will end up at LM within a few calculations. So here's the first part of solving out this triangle over here on the right-hand side. Sine of angle L divided by its opposite side length, which from angle L's perspective, this guy right here, 4.6 is on the opposite side. So sine of L divided by 4.6 must be equal to sine of 93 divided by 7. So to get angle L alone, I'm going to multiply both sides by 4.6 and hit it with inverse sine. So L should be equal to inverse sine of 4.6 sine 93 degrees, then divided by 7. So if you do that calculation, what do you get out there for angle L?
Angle L is 41.01.
Correctly applying the law of sines here should give us, yep, that angle L is equal to 41.01 degrees. And so I'll go ahead and toss that on the diagram because, again, sometimes it's hard to see why this information is useful to us. 41.01 degrees. Why do we care? How does that get us to LM?
Because now we can do third angle theorem, and then using that third angle, we can use law of sines again to get.
Keep in mind that if you have two angles of a triangle, you actually have all three, because all of these have to add up to 100. If this is 41.01 and 93, and they sum to 180, then this other angle right here has to be 45.99. And now that we have this angle, I can get the final side that we wanted, LM, by using the law of sines one more time. This statement is a true and useful feature of the law of sines, so I'll use that same ratio again, just because it has no rounded numbers in it. So it's sine of 93 over 7 is going to be equal to sine of 45.99 degrees, then divided by our desired side length, LM. Cross multiply and divide to get LM alone, and I believe you will find that LM must be equal to 7 times sine of 45.99, then divided by sine of 93. And this will give us our final answer here. Make sure that you are still correctly using your calculator at home to do trigonometry. Make sure your calculator is in degrees mode and that you don't forget SOHCAHTOA, the law of sines and the law of cosines, because as I'll continually remind you guys until summer hits, it's a big topic of study next year.
I got 5.04.
Correct. I think this is an interesting problem because the circle property that we're using is really just the first step, right? It's the missing angle that you need to do trigonometry. But then after that, from there, the rest is just old skills. The rest is just correct application of the law of sines. One other thing, how big does the diameter of this circle have to be? You can't calculate it with the given information, not easily at least. You'd have to do some differential calculus to get exactly what the diameter is. But tell me something interesting about the diameter.
It has to be greater than 7.
Very good. That's exactly what I'm getting at. A diameter is always the longest chord within a circle. So if this thing isn't the diameter, you know that whatever the diameter is, it's got to be bigger than at least 7. Anyway, that's it for today's two-part warm-up. Are there any questions on either of these two questions?
No.
No? Okay. A quick rundown of Tuesday's quiz. And then if you are already done and uploaded with the 10.4 homework, after I do this breakdown, that means you can head out and start enjoying your 3-day weekend. Yeah. The weather's real nice. I personally can't wait to eat lunch today. And then we'll go chill outside, man. I'm gonna take my skateboard out and go get some fresh air. Actually, you know what has been one of the suckiest things about this whole like COVID world, man? Sucks wearing a mask with glasses, right? Y'all know what I'm talking about? What happens when you wear a face mask with glasses?
Foggy.
Then nothing shows except your forehead.
It's so annoying.
Oh, I mean, that part I don't care about. I mean, I'm handsome no matter what. Like, I'm tripping on that part. It's the fog, yeah, of like
The
a
glasses get
tail.
all foggy.
Yeah, and then your glasses get all foggy, which is big because I wear like sunglasses all the time. I'm hating this like either. Yeah, I just hate constantly being outside with sunglasses that are foggy. So now I've like been not wearing sunglasses, and I don't know. I hate the sun. I think it's too bright. Anyway, that's neither here nor there. Here's what I'm asking y'all to do for me from each section. So item number 1, that first section was just about circles and circumference. So from section 1, I'm going to ask you guys to correctly manipulate and use the fact that circumference is equal to 2 pi r, which is equal to pi d. There will be a couple of these questions. Just be ready for any manipulation. That is to say, given any one of these numbers, you should be able to calculate the other. Given a circumference, you should be able to calculate radius. Given radius, you should be able to calculate diameter, blah, 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 right? On top of that, please be sure that you're very clear about the usage of the word approximate versus exact. Just like with the trig stuff, I'm going to be a crazy person about giving points for questions based on the way that they're requested. If you give me a decimal, that's an approximate answer. If the answer is in terms of pi, if the answer is 1/3 pi, that is exact. For the most part, I'll be asking you for exact answers, and for all of those exact answers, leave your answer in terms of pi. Also, the bonus question is going to be coming from section 1. I'll come back to that at the end. Item number 2. In section 2, we talked about arc measurements and arc length. Wait. I'm sorry. In section 2, we talked just about arc measurement and what arcs are. So please keep in mind that arc measurement is the angle made between two segments. Sorry, the angle made that intercepts an arc with two radii. So this is to say, if I wanted the arc of measure AB, we would need to know what the center of the circle is. And so the measurement of arc AB is equal to angle ACB. That this guy's measurement to measure this arc is actually to take this angle. Is that part okay?
Yeah.
Yeah.
And this leads us to two really interesting, important properties about this. The sum of all arcs of a circle has to be equal to what?
360.
Better be 360. If you travel 360 degrees by spinning around once, then this arc plus this arc plus this arc plus this arc back to here, those arcs need to sum to 360. Very common to be given partial arc data and then need to use that feature in order to get the other measures. And this is also the section where we get arc length. That's where we're actually talking about lengths. Arc length equation requires knowing how big this circle is. So that's where we start mixing in the use of the radius r. And here's what derives the arc length equation, and I'll also write down the simplified version. That is to say that the actual curvilinear length of AB is going to be equal to, well, the circumference, because the circumference goes all the way around the circle. So that's going to be equal to 2 pi r, then multiplied by the fraction of the circle's circumference that I'm asking you for. So we said before that, well, a circle has 360 degrees. So if we know the arc measurement, then that's going to be a fraction out of 360 that tells us how much circle I want. If it's a 90-degree cut, that's 90 over 360, which is 1/4 of the circle. If it's 180, right, that's half the circle because it's the diameter. So if you go from here to here, that's 180 degrees. 180 over 360 is 1/2. And so if you wanted the length of that semicircle, then I'm asking for half the circumference.
If you
The way
do
that we, yes?
sorry, if you do it like over 180, then can you not put the 2 there in 2 pi r?
Uh-huh.
So
Yep.
it's the same thing.
That's the part that I'm explaining now, and that's the part I'm
Oh,
writing after this. Yeah. That if I want the fraction of the circle, that this is measurement of arc AB, then divided by 360 degrees, this gives me the fraction of the circle. This is just the justification for why this relationship is true. But as you know, we derive equations and we simplify things and we do algebra as we move along. Should you choose to simplify this 2 with this 360, then the way that you'll typically see the arc length equation written in textbooks is that the arc length AB is equal to pi times r times the measurement of the arc itself, which again is that central angle, all then over 180. But there is no mathematic difference between these two statements. Just like with the circumference, not only do you need to be able to take an arc measurement and use that to calculate an arc length, you should be able to do it backwards and use arc length to calculate arc measurement and vice versa. Part 3, we talk about arcs and chords here. So arcs and chords. This section is pretty bare. It's pretty straightforward, though it has really just two interesting relationships in it that we concern ourselves with in this section. The first one is very duh. The second one is a little less duh, but the way in which you use it goes back to being very duh. Here are the two features drawn in one diagram that section 3 asks you to know. Because of triangle rules, if I have two congruent chords in a circle, if I know that these chord measures are equal, then I know that the measurements of their arcs will also have to be equal. That's just because both of these, if you actually drew in the lines that go to the center, this would produce two congruent triangles, and if the triangles are congruent, they have all the same angles, one of those angles being this exterior arc measure. So if two chords within a circle are congruent, the arcs that they contain are also necessarily congruent. The other property here that we want to know about is that if I have a diameter that goes through the circle, and it happens to perfectly bisect a chord, which is to say this length here and this length here are the same, then it is going to force the angle that it makes with the diameter to be 90 degrees. And of course, the main reason why we're interested when things are 90 degrees is what? Why would we care about that 90-degree angle?
It means that you can use the Pythagorean theorem.
Very good. It means that depending on what additional segments are in here, and here's one that I basically guarantee on this quiz, this guy, once you know that something within a geometric figure is 90 degrees, it opens the door to trigonometry. It opens the door to the Pythagorean theorem or SOHCAHTOA, and then suddenly we can learn so much more about what's going on the inside here. Those are the only two properties that I'm going to ask you to use, and the questions for this section are going to look very much like the ones from the homework. And then for this last one, section 4, the one that we talked about, I don't want to draw it out again because we did the notes yesterday. Yeah. But in section 4, we talk about the inscribed angle theorem, which is to say that if I have some circle, I will draw the inscribed angle theorem, but not the special cases. I think y'all should have those down. The inscribed angle theorem simply states that whatever angle this is, if it is an inscribed angle, angle x, then this is exactly 1/2 of the arc measure of the arc that it intercepts. So from here to here, this arc measure must be 2x, where of course arc measure, where my center at? Here it is. Where of course arc measure is defined as the angle made with the center of the circle itself. So that 2x arc measure is actually this angle right here, that central angle. And from this, we were able to derive two special cases that you'll be responsible for using on Tuesday. Special case 1, triangle with a diameter. Again, triangle with a diameter. The reason why that's cool is that a diameter's arc measure is 180. Half of 180 is 90. And so if you have a triangle which is formed within a circle with a diameter, you know it's a right triangle, you know we're doing trig. And then the other one is for an inscribed quadrilateral, because of some very clever algebraic substitution, trickery, and manipulation. We know that the opposite angles of a quadrilateral, so this one is a right triangle, and then for a quadrilateral, opposite angles are supplementary. And in terms of Tuesday's quiz, I only have 12 questions for you here. The 12 questions are designed very much like the questions in the homework, and you should know that those 12 questions will flow out in the same order that these topics are gone in. So on the quiz, if you get lost, look at what fourth of the test you're in. If you're in the first one, fourth, we're probably on section 1. The second one, fourth, probably section 2. The third quarter, you'll probably be on arcs and chords. And these questions here will be at the end. So if these stump you, do what we did in today's warm-up and start labeling bits and pieces and do your best from there. Last thing is the bonus question, like I mentioned, would be from section 1. That's why this little asterisk is here. For the bonus, I'm going to be asking something about pi. On that first day of notes, and feel free to go back to the YouTube channel, I talked about some historical information about how pi evolved over time, that pi is a irrational number and what that irrationality means, and that there are various equations which generate pi. I'm going to be asking either some trivia or some math about pi that is not necessarily about circles. Now, I'm not asking you to memorize anything crazy, but but please do have some control of the notes about the history or equations which generate pi. I'll be asking about that in the bonus question. Are there any questions about Tuesday's quiz?
No.
Cool. If you got the homework turned in, you may now begin your 3-day weekend a little bit early. You have a nice 3-day weekend, and I'll see you on Tuesday.
Bye.
Otherwise, feel free to hang around and work on the homework and get it uploaded before you head out so that it's done and put away.
Mr. Robinson, I have one question for the homework and then I'm like done.
Sorry, what?
I have one question about the homework and then I'll be done.
Dope. What's that? What's the question?
Okay, so number 4 on the first page on 23, I didn't really get how to do it.
Number 4 on the first and 23. Oh, okay. Yeah. So you didn't get it because it was like today's do now, and I didn't show you guys the outline of like what the logic is for the questions with the hourglasses. Let me copy it, and then we'll walk through it together. Those hourglass type questions are really common because I think they take advantage of the inscribed angle theorem in a pretty clever way. So in question 4, this is the hourglass question with WTUV, right?
Yeah.
UV, and they're telling us that this is 3x plus 4. This is 30. This is 2x plus 9. So here's the deal, right? There's a direct relationship between the measurement of an inscribed angle and the measurement of the arc that inscribed angle intercepts. That's what allows us to solve this problem. Without that information, this wouldn't be doable at all. So let's go ahead and look at here, angle T, and then this line goes out, this line goes out, and it inscribes the arc VU. We can do the same thing here for the angle formed here at W, what 2x plus 9 is equal to. If you trace its lines outwards, you'll notice they intercept the exact same arc. If two inscribed angles intercept the same arc, they need to be equal to each other. There's really no way around it. And that's what provides us with enough information to actually complete basically all of the angles here. And so I won't just solve the question. I'm also going to like beat this question to death. There's enough information here to fill out almost all the angles the same as the warm-up. So we can get both of these by setting them equal, because again, they intercept the same arc.
Yeah, and then you divide it by 2. The answer?
So it's 2x plus 9 is equal to 3x plus 4. How do we solve for x here?
You do minus 4, like, and you
then?
get 2x plus 5 equals 3x. So then you do minus 2x, and you get 5 is equal to x.
So if you take that and plug it back in, what is this?
It's 15 plus 19.
And the same as here, if we did the algebra correct, that is also 19. So that's cool. That also tells us what this arc measurement is, right? What does this arc measurement need to be?
It's 19 times 2.
Yeah, so this is 38 degrees of arc measurement. So then the same thing is true for the opposite side here. So we could say that V, this angle, TVW, it goes out and it intercepts arc WT. So because angle U here goes out and intercepts the exact same arc WT, that tells me that this guy is also 30 degrees, which I believe is actually the answer to that question, the first one that you asked me, number 4.
Yeah.
It's just 30 degrees because it intercepts the same angle as this arc, or as this angle right here.
Yeah.
And with the triangle angle sum theorem, that can also give us all of the angles here on the inside, should that... I'm being this detailed because this is the kind of thing I'm going to ask on the quiz. I'm going to give a simple setup and ask for all the values. The triangle angle sum theorem would tell us that because these all have to add up to 180, that this inside angle here is 131. Vertical angles gives us that the opposite side is also 131. And then since all of the angles in a circle have to add up to 360, that also tells us that this is 49 and that this is 49. And now we have defined basically all of the angles and arc measures possible here in this diagram.
131 because 19 plus 30 is like, and then you do like 180 minus 19 minus 30.
Precisely. Triangle angle sum theorem. Yep.
Okay, thank you.
Yeah, that's everything there. So yeah, big trick. If two inscribed angles intercept the same arc, they're necessarily congruent.
But you can't find the arc WV, the measure of it.
You know, there might be another rule or another theorem just for that. And I'm like, I've been trying to stretch my brain since we did the warm-up. I feel like it should be possible. They seem like they are well defined, but I can't think of a straightforward way to justify that.
Why not? If you found that the arc, like that arc measures 131, then isn't arc measure WV 131?
Say that again.
You know how you found that like 131 and 131 like in the middle?
That's not the center of the circle.
Oh, okay.
If that was the center of the circle, if you knew that for sure, then yeah, then it would meet the definition of an arc measurement. But if the center of the circle, and actually I guess I drew it, so I know where it is. The center of the circle is actually right here. And this point isn't that point. So it would be the angle that you would get if you drew it from here to here, and that angle would be different than this angle.
Oh.
Yeah. It feels like there should be a way to figure out what these two numbers are. I don't see it. I'm not sure it is possible, at least not with the level of math that we're doing. I'm sure there's some really like elegant calculus technique that you could use to quickly get those other two arc measures. But I think with the basic rules that we're stuck working with, there's not a great way to quickly get these other two arc measurements. But if I think of a way, I'll let you know. Or if somebody else figures it out, they'll get extra credit and then I'll teach it to the rest of the class. Oh boy, I'm so excited to go for a skate. I haven't been on my skateboard in like 2 weeks.
Wait, also for number 6, like there's 2 different variables, so how do you solve that?
By setting 2 of them equal first. So assuming we're looking at the same diagram. Oh, no. The 2 sets of variables don't interact with each other. Because of the way that the lines intercept the arcs, 6y minus 2 is equal to 5y plus 8. And then on the opposite side, 6x minus 3 is equal to 7x minus 11.
Yeah, B and C are equal and A and D are equal.
Yeah, but those give you 2 separate problems that only use 1 variable each. There's no solving that involves both.
I accidentally mixed up like which ones are equal before.
Yeah, big fan when you're doing this stuff to make sure that those mistakes don't occur. Super big fan of color coding because sometimes it's hard to see that stuff going on at the same time. But if you color code it, it's pretty clear that this and this go to yellow. That this and this go to yellow. I think it makes it easier to see which pieces go where or whatever while you're solving, you know? Big fan of using colors in general. You should always use colors whenever you're trying to code out a problem that you're solving. That's why I'm a big fan of this Bic multi-pen, which is kind of a standard at NASA or whatever. It's just so nice to have blue, green, black, and red ready to go in one pen.
Okay, Mr. Robinson, I'm gonna go because I finished.
Okay, you have a very, very nice long weekend.
You too.
I will. I'll go ride my skateboard and hope I don't get a head injury. Head injuries are bad, if you didn't know, kids. Oh boy, I got a big flood of homework of seniors turning stuff in late. Better late than never. Okay. Well, all of you have a very nice 3-day weekend, and if you have any questions on the homework, feel free to email me or ask them now if you have them.
Okay, have a nice weekend, Mr. Robinson.
You too, buddy. Take it easy.
All right.
Peace.